Have you ever wondered how MRI machines create such detailed images of our bodies without using X-rays? It's all thanks to magnetic fields produced by loops of current. Just like bar magnets, these current loops generate magnetic fields, but with a twist. When current flows through a circular loop, it creates a field that mimics the behavior of a magnet with a clear north and south polarity. Now imagine the axis, a straight line cutting through the center and perpendicular to the loop. That's where the real magic of symmetry kicks in. On this axis, the magnetic contributions from every tiny segment of the loop add up beautifully, giving us a neat, measurable magnetic field. And believe it or not, this setup is the heart of many real-world technologies, from magnetic coils to wireless chargers. To calculate this magnetic field, we turn to a key principle, the Biot-Savart law. It's like the cousin of Coulomb's law, but for magnetism. According to this law, the magnetic field dB at a point in space due to a current element IDL is given by this formula, dB equals mu naught divided by 4 pi multiplied by IDL cross r hat over r squared. Here, mu naught is the permeability of free space, r is the distance from the current element to the point, and r hat is the unit vector in that direction. Now here's the important part. When we apply this law to a circular loop, symmetry saves the day. All the radial components of the magnetic field cancel out, and only the axial component survives. That's what we'll calculate next. Let's build our derivation. Picture a circular loop of radius r, carrying a steady current I. Now focus on a point P on the axis at a distance x from the center of the loop. If we take a small current element on the loop and apply the Biot-Savart law, we find that the vertical components cancel due to the loop's circular symmetry. Only the components along the axis remain. Using geometry, we find that cos theta equals r divided by square root of r squared plus x squared. That's the projection factor for the axial field. This is where the symmetry of the loop allows us to integrate all the contributions cleanly. Now, let's get to the result. When we integrate the Biot-Savart expression for the entire loop, we arrive at a beautiful, compact formula. D equals mu naught I r squared divided by 2 times the quantity r squared plus x squared raised to the power 3 by 2. This formula gives us the magnetic field at any point x along the axis of the loop. At the very center of the loop, where x equals 0, it simplifies to B equals mu naught I by 2r. Simple and powerful. And as we move away from the loop along the axis, the field decreases rapidly. This knowledge is crucial in designing devices like Helmholtz coils, where a nearly uniform magnetic field is needed between two loops. Here's a deeper insight. A circular current loop behaves like a magnetic dipole. The loop has a magnetic moment m, given by I multiplied by A, where A is the area of the loop. And just like electric dipoles, magnetic dipoles have a characteristic field pattern. The direction of this magnetic moment follows the right-hand rule. Curl your fingers along the direction of current and your thumb points in the direction of the magnetic moment. Now, at points far away from the loop, where x is much greater than r, the loop's field mimics that of a bar magnet. The expression simplifies to B approximately equals mu naught over 4 pi multiplied by 2m over x cubed. This dipole behavior isn't just theory, it's used in everything from magnetic compasses to understanding the Earth's magnetic field. Let's apply our knowledge with a real example. Suppose we have a circular loop of radius 0.1 meters carrying a current of 5 amperes. We want to calculate the magnetic field at a point 0.2 meters away on its axis. Using the formula, B equals mu naught I r squared divided by 2 times r squared plus x squared raised to 3 by 2. Let's plug in the values. Nu naught is 4 pi times 10 to the power minus 7, I is 5, R is 0.1 and X is 0.2. Do the math step by step and you get B equals 7.1 microtesla. So even at a distance, the loop creates a measurable field. This is the kind of calculation used when designing magnetic sensors and diagnostic equipment. Let's quickly revise what we've learned about magnetic fields from current loops. We began with the idea that a circular loop behaves like a tiny magnet. Using the Biot-Savart law, we derived the expression for the field on the axis of the loop. We saw how symmetry makes our calculations simpler and how the formula B equals mu naught I r squared over 2 times r squared plus x squared to the power 3 by 2 beautifully captures the magnetic field at any point on the axis. We also learned that a current loop acts like a magnetic dipole and how this concept appears in real life, from electromagnets to MRIs to atomic physics. I hope you now have a clearer understanding of how currents generate magnetic fields and how loops shape them in elegant, predictable ways. See you in the next session with another fascinating concept of physics.